Hello and welcome to the Escape Velocity Preflight for second hour Mr. Michael Jack's AP Physics class. Today we are going to be talking a little bit about escape velocity as well as universal gravitation and orbits. This is the group of Daniel Sudaseri, Max Threlkeld, Cam Greer, and Patrick Mucci. To begin, it is important to establish some background on the subject we are focusing on. So first, we need to look at the scientist who discovered it, which is Isaac Newton. He played a huge role in a lot of concepts revolving around gravity and working with planets. And this background was helpful in producing the definition of what escape velocity is, which is the velocity needed to escape the gravity of a planet or star. From here, we can discover more in terms of different gravities of planets and the velocity needed to escape them. Next, in terms of escape velocity, we need to look at how this equation was derived from energy and see how we can apply this to different concepts. So first, we need to start with the conservation of energy, which is the kinetic energy of an object must be greater than the potential of gravity of the planet. So it's important to realize that in order to escape a planet, you need to have a velocity greater than the potential to overcome this gravitational field. So the kinetic energy, or 1/2 mv squared, where m is the mass of the object trying to escape and v is your velocity, must be greater than the gravitational constant, which is Planck's constant, 6.67 times 10 to the negative 11th, times the mass of the object times the mass of the planet over the radius. Then, from here, we need to look at v squared equals 2gm over r. That's simplified a little more. And then after that, take the square root, and we finally get the escape velocity is the square root of 2gm over r. This is important because you can see how the mass of the object does not matter in this equation. So it doesn't matter how much an object weighs, whether it be very small or large, it takes the same velocity as any other object. So if the radius of a planet is greater, then its escape velocity will be less, whereas the mass of the planet is greater, then its escape velocity will be less because of this equation that we see. Now, it's also important to look at different environmental factors regarding escape velocity, because in the equation, it's important to notice that air resistance is considered negligible, as well as the rotational energy of the object trying to escape the planet is disregarded as well. So this equation, v equals the square root of 2gm over r, even though it is scientifically, conceptually correct, it does not directly apply to an object trying to escape the gravity of a planet, because in most cases, when dealing with problems like these, we need to take a look at air resistance, because it is a huge factor in many velocity problems, because even though it may not be sometimes possible to calculate this, it plays a huge role because the object will be slowed down a good deal because of the resistance of air. And in addition to this, the rotational energy is not taken into account. So if this object is rotating at all in the air, this energy will take away from the kinetic energy of the object, and some of this energy will be lost, so its velocity needs to be greater in this regard again. So these different factors play a huge role in changing what the exact escape velocity of an object is trying to escape the gravitational field of a planet. Finally, to wrap this all up and show the escape velocity connection to an important unit in the AP Physics 1 criterion and kind of workbook, is connection to universal gravitation and orbits. So you can see that this equation from escape velocity can also be derived from the force of gravity equation, which is gmm over r squared, equals ma. So the force of gravity equals the mass times acceleration of an object trying to escape the planet, and then the acceleration is actually a circular acceleration, so v squared over r, and then because we're talking about circumference, and then from this we can solve for escape velocity. So this is important because this equation can be used to find the fields of planets, as well as what the force of gravity on the planet is, because not every planet has the same force of gravity as Earth, which is 9.81 meters per second, but depending on the radius and the density of the planets, the gravity may differ. This is important to take note of, because sometimes it is not. Sometimes we forget it when looking at the different aspects of a planet or star. Now, in addition to this connection, why is gravity important? Because one, we wouldn't have our 2 feet on the ground without it, and another is that it is still a concept that we are trying to grasp. And even though we've had some research being done, and we found the one star earlier this year where gravity was expressed as waves, we still are not entirely sure of this concept. And we are fascinated by it, but this escape velocity connects to it pretty well, because we're able to look at the velocity of an object to escape this gravity. But it's also important to see, when looking at terminal velocity and seeing an object fall, how it accelerates. So there's so many different concepts with gravity that are discussed in the AP Physics work, and gravity is just a very important concept to learn.